Welcome to this fascinating exploration of the science behind cooking pasta. Today we're going to debunk a common kitchen myth and understand the physics and chemistry that govern why oil and boiling water doesn't prevent pasta from sticking. Many people add oil to their pasta water, believing it will prevent the pasta from sticking together. But does this actually work? Let's examine the science. The first important fact is that oil floats on water. This happens because oil is less dense than water. Typical cooking oils have a density of about 0.92 grams per cc, while water has a density of 1.0 grams per cc. Here's what happens in your pot. The oil forms a thin layer on top of the water surface. The pasta pieces are completely submerged in the water below, never coming into contact with the oil layer during cooking. Oil and water are immiscible, meaning they don't mix. This is due to their different molecular structures. Water is polar, with molecules that have positive and negative ends. Oil molecules are nonpolar hydrocarbons. The rule, like dissolves like, applies here. Polar water molecules are attracted to each other through hydrogen bonding, and nonpolar oil molecules cluster together, leading to phase separation. Let's discuss surface tension, which is crucial to understanding this phenomenon. Surface tension gamma is defined as force F per unit length L. For water at 100 degrees Celsius, the surface tension is approximately 59 millinewtons per meter. This relatively high surface tension means water molecules at the surface experience a strong, cohesive force pulling them together. Here's a key question. Why doesn't the oil coat the pasta as it moves through the water? The answer lies in both density and miscibility. During boiling, the pasta is constantly moving in the water due to convection currents, but it stays submerged because the pasta is denser than water. Fresh pasta has a density around 1.1 to 1.3 grams per cc. The density hierarchy is: pasta is greater than water, which is greater than oil. This means pasta sinks, oil floats, and they never really interact during cooking. So if oil doesn't help, what actually causes pasta to stick? The answer is surface starch. Pasta is primarily made from semolina wheat flour, which is rich in starch molecules, particularly amylose and amylopectin. When you look at the surface of uncooked pasta under a microscope, you see it's covered with starch granules. These are the molecules that will cause problems. When pasta is heated in water above about 60 degrees Celsius, a process called starch gelatinization occurs. The starch granules absorb water, swell, and some of the starch leaches out into the cooking water. The gelatinization temperature for wheat starch is approximately 60 to 70 degrees Celsius, well below the boiling point of water at 100 degrees. As starch molecules hydrate, they form a sticky, gel-like coating on the pasta surface. When two pieces of pasta touch, this sticky surface causes them to adhere to each other. Let's examine the actual mechanism of pasta sticking in more detail. Starch molecules contain many hydroxyl groups, which are polar. These groups form hydrogen bonds with water molecules during hydration. The energy of a typical hydrogen bond is about 20 kilojoules per mole. While individual bonds are weak, the collective effect of thousands of bonds creates significant adhesion. When two hydrated pasta surfaces come into contact, the starch molecules can bridge between them, creating a network of hydrogen bonds that holds the pieces together. This diagram shows starch molecules forming bridges between two pasta surfaces. These bridges are what cause the sticking. Interestingly, adding oil after draining the pasta does work to prevent sticking. But why does this work when oil in the water doesn't? When you add oil directly to drained pasta, the pasta is no longer surrounded by water. The oil can now make direct contact with the pasta surface. The oil forms a thin, hydrophobic layer on the pasta surface. This layer prevents the hydrated starch on one piece from making hydrogen bonds with the starch on another piece. The coefficient of friction for oil is much less than for hydrated starch. The oil acts as a lubricant, allowing pasta pieces to slide past each other easily. By creating a slippery interface, oil dramatically reduces the adhesion forces between pasta pieces. This is purely a mechanical effect, not a chemical one. This situation presents an interesting paradox in surface chemistry. Let's explore the concept of surface energy. The surface energy between a solid and water is generally lower than between a solid and air. This is why wetting occurs. When oil coats the pasta after draining, it replaces the water that was at the surface. This changes the interfacial energy balance. The work of adhesion between two surfaces is given by gamma 1 plus gamma 2 minus gamma 12, where gamma 12 is the interfacial tension. Oil dramatically lowers the interfacial tension between pasta pieces, reducing the work required to separate them. This is why oiled pasta doesn't stick. Let's do some numerical estimates to quantify these effects. Studies show that approximately 2 to 4% of the pasta's dry weight is lost as starch to the cooking water. For 100 grams of dry pasta, that's 2 to 4 grams of starch. This starch loss creates the sticky surface layer that causes adhesion. The hydrated starch gel layer on pasta is estimated to be about 10 to 50 micrometers thick, based on microscopy studies. This thin layer is enough to cause significant sticking because starch is highly adhesive when hydrated. You only need about 1 to 2 tablespoons of oil for 500 grams of pasta. That's approximately 15 to 30 milliliters, which forms a layer just a few micrometers thick. This small amount is sufficient because oil has low viscosity and spreads easily across the pasta surface when tossed. Let's consider the fluid dynamics during pasta boiling. The Reynolds number tells us about flow patterns. The Reynolds number is defined as rho VL over mu, where rho is density, V is velocity, L is characteristic length, and mu is dynamic viscosity. During vigorous boiling, the Reynolds number is typically greater than 4,000, indicating turbulent flow. This turbulence keeps pasta pieces moving and separated during cooking. In turbulent flow, pasta pieces are constantly tumbling and moving, which actually helps prevent sticking during the cooking process. This pasta phenomenon has interesting analogies to other systems. Let's explore some connections. Just like oil in pasta water, oil from spills floats on the ocean's surface due to density differences. The oil doesn't mix with seawater and forms a surface layer that can harm marine life. This is similar to our pasta pot. The oil stays on top, the water is below, and things in the water don't get coated by the oil. The sticking mechanism of pasta is essentially the same as how starch-based adhesives work. Stamps, envelopes, and paper glues often use starch for adhesion. In both cases, when starch is hydrated and pressed between surfaces, the hydrogen bonding network creates strong adhesion. The mechanism is identical. Oil on drained pasta works similarly to Teflon coating on non-stick pans. Both create a hydrophobic, low-friction surface that prevents adhesion. Teflon and oil both work by reducing the interfacial surface energy and coefficient of friction, making it difficult for materials to stick. What are the practical implications of understanding this science for cooking? First, don't waste your oil by adding it to boiling water. It won't help prevent sticking, and it just sits on the surface doing nothing. Instead, use plenty of water and maintain a vigorous boil. The turbulent flow keeps pasta separated mechanically. Use about 4 to 6 liters of water per 500 grams of pasta. Stir the pasta occasionally, especially in the first 2 minutes when surface starch is most actively gelatinizing. This prevents pieces from settling and sticking together. If you want to prevent sticking after cooking, add oil only after draining. Toss the pasta thoroughly to ensure even coating. Alternatively, skip the oil entirely and immediately toss the drained pasta with your sauce. The sauce serves the same anti-sticking function as oil. While we're discussing pasta water, let's briefly address another common ingredient: salt. People often add salt to pasta water, but does it affect sticking? The short answer is, not really. Salt is added primarily for flavor. It seasons the pasta from the inside as it cooks. The amount typically used, about 1 to 2 tablespoons per 4 liters, is not enough to significantly change the water's properties. Salt does raise the boiling point through boiling point elevation, where delta T equals Kb times molality. But with typical salt amounts, this increase is less than 1 degree Celsius. Salt does not prevent sticking because it doesn't affect the starch gelatinization process or the interfacial properties between pasta surfaces. Let's explore a more advanced concept that helps explain oil's effectiveness: the contact angle. The contact angle theta is given by Young's equation. Cosine theta equals gamma SV minus gamma SL, all divided by gamma LV, where S is solid, L is liquid, and V is vapor. Water on pasta has a small contact angle, typically less than 30 degrees. This means water spreads easily and wets the pasta surface well. Oil on pasta has a larger contact angle, around 60 to 80 degrees, meaning it doesn't wet the surface as completely but still forms a continuous coating. This partial wetting is actually ideal. The oil forms a protective layer without being absorbed into the pasta, maintaining a hydrophobic barrier on the surface. Different starches have different sticking properties based on their molecular composition. Starch consists of two main types of molecules: amylose, which is linear, and amylopectin, which is highly branched. Wheat starch, which is what pasta is made from, typically contains about 25% amylose and 75% amylopectin. Higher amylose content generally leads to more retrograde starch formation and thus more sticking. Amylose molecules can align more easily than branched amylopectin. Let's address some common questions about this topic. Some professional chefs add oil to pasta water not to prevent sticking, but to reduce foaming and prevent boil-over. The oil reduces surface tension slightly and can help suppress foam formation. Yes, pasta shape matters. Long, thin shapes like spaghetti have high surface area to volume ratios and are more prone to sticking. Short, thick shapes like rigatoni stick less because they have less relative surface area. Fresh pasta contains more moisture, typically 30 to 35%, compared to dried pasta at 10 to 12%. This higher moisture content means more surface starch is readily available for gelatinization. Absolutely. The best method is proper technique, sufficient water, vigorous boiling, occasional stirring, and immediate sauce application after draining. No additives are necessary. Let's examine why oil and water don't mix from a thermodynamic perspective. The Gibbs free energy of mixing is delta G equals delta H minus T delta S. For mixing to occur spontaneously, delta G must be negative. For oil and water, the enthalpy of mixing delta H is large and positive. Breaking the hydrogen bonds between water molecules requires significant energy that isn't recovered. While mixing would increase entropy, this entropy gain isn't large enough to make the overall free energy negative. Therefore, oil and water remain separated. This thermodynamic unfavorability is why oil and water spontaneously separate into distinct phases, with oil floating on top due to its lower density. Let's summarize the key scientific principles we've covered. Adding oil to boiling water doesn't prevent pasta from sticking because the oil floats on top and never coats the submerged pasta. Pasta sticks because surface starch gelatinizes during cooking, forming a sticky hydrated layer that creates hydrogen-bonded bridges between touching pieces. Oil added after draining works because it directly coats the pasta surface, creating a hydrophobic lubricating layer that prevents starch-to-starch contact. This everyday kitchen phenomenon beautifully demonstrates fundamental principles of density differences, liquid miscibility, surface energy, and hydrogen bonding. The most effective way to prevent sticking is through proper cooking technique, ample water, vigorous boiling, stirring, and immediate sauce application.